Okay, here we go.
All right. Thank you. And I apologize to everyone. I'm having some network issues, which is why we're getting started slightly late. So let me thank June for coming to speak to us today. June is at Stanford doing a PhD, I think, with Moses and Nima, and has been doing a lot of exciting work on various things to do with discrete distributions. And June will tell us about entropic independence today. And June, I'm going to try to pay attention to the chat, so I'll tell you if there are questions along the way, so people can write questions there.
Sure. Yeah. Thanks, Rasmus. And I guess people can ask question directly if okay. Well, just to interrupt. Feel free to interrupt the talk and ask question. Thanks. So yeah, thanks Rasmus for the invitation and also for the introduction. So as Rasmus just mentioned, I will talk about our new work called Entropic Independence, and specifically we will talk about the application to the Ising models. And this year, joint work with my advisor Nima Anari, Vishal Jan, Fred Kohler, and Huy Pham. Like I guess we are all at Stanford, except for Fred, who will join Stanford in the spring. So first we will go over the motivation for this, the application and motivation for this work. So we will talk about the Ising model and the problem of sampling from the Ising model, and then some basics about analyzing the runtime of a common sampling algorithm called the Glauber dynamics. So first so the Ising model is defined follows. So this is a model of magnetization of atoms in the material. Each atom is assigned a spin either plus or minus, and the distribution is over all plus minus configuration of the atoms. So in this picture, I color the atom with plus as blue and the atom with minus spin as gray. So this is the plus atom, the plus atom and the minus atom. So the distribution is characterized by an interaction matrix J and an external field H. The density function mu evaluated on a particular configuration sigma is defined by the exponential of the Hamiltonian, where the Hamiltonian is sigma times J times sigma transpose, so 1/2 of that. So this exactly this expression plus 8 times plus the dot product of sigma and H. And so for this model, what we care about is to sample from this model or to approximate the partition function, which is the sum of this mu sigma over all configuration sigma. And this task of sampling or approximating the partition function is important in physics and later has application in other fields such as the study of social network and social choice. So this model is also alternatively known under the name of spin glass model, and people study it to understand the structure of material. So in this picture, you can see that when the material is very regular, then the spin configuration is like sort of like it only had either plus or minus spin, and then when when the material is very non-structured, then you have very random or diverse configuration. And this spin glass model was studied by Giorgio Parisi, Michael Talagra, and Francisco Gura. And this year, I think Parisi just won the Nobel Prize in Physics for his work in spin glass or Ising model. And for neural network, Ising model is also useful to understand a certain neural network called the Hopfield model, which is studied as a model for human memory. And for social choice, this Ising model is useful to study voter system, where each person is modeled as an atom, and then he had two kind of vote, either plus vote or minus vote, and his voting choice is influenced by his neighbor. All the people he interact with. So for the Ising model, like there was some specific variation that we care about. So one of them is called the Curie Weiss model, where the interaction matrix J is sort of the all-one matrix, or like scaled by a factor 1/n. So n here is the number of vertices in the Ising model. And so this is somewhat an older and more simple model, and people understand it like quite well. And then the more recent model that I think studied by Michael Telegraph and Parisi is something called the Serrington-Kirkpatrick model, where J is now like so each n child of J is identically and independently distributed according to the Gaussian distribution with parameter beta square divided by n. And the parameter beta here is something called the inverse temperature. I will explain the intuition later, but so yeah. So okay, the task we care about with Ising model is to sample from it, and by sampling I mean to generally for any distribution mu, sampling means to produce to produce x in the support of mu according with probability according to that is proportional to the density function mu x. But usually this task is very hard. This task of like exactly like produce x according to the distribution is quite hard. And then somewhat easier task is to approximately sample. So instead of outputting like x according to this px, we output it according to like tilde px, so that the total variation distance between p tilde and p is like at most some 1/n to the 100. So this is like so it's like we want to produce p tilde that are close to p that is very close to p in total variation distance. And total variation distance is defined as 1/2 the L1 norm or difference between like two probability distribution. Okay, so to sample from the Glauber from the Ising model, one very popular tool is called the Monte Carlo Markov chain method. The idea is to iterate some probabilities through starting on from some given configuration, and this probability through is called a Markov chain. So for a suitably defined Markov chain, after say running it for t iteration, we will reach the desired distribution. And we say t is the missing time of the Markov chain. And by reaching the distribution, I mean that like the distribution after t step here will be very close to the target distribution mu in terms of TV distance. So one very natural choice of Markov chain is called the Glauber dynamics. So it operates as follows. At each step, it starts this configuration. It chooses an atom and update the spin of that atom according to the marginal distribution of mu condition on the remaining atoms. So, for example, say we are at this configuration where like 1, 2, 3 had plus spin and 4, 5 had minus spin. We choose atom 3 to update. So we update 3 to blue here with probability proportional to mu that spin 3 being plus condition on the remaining atom 1, 2, 4, 5, and similarly update it to minus condition on the state of the remaining item. And we iterate this through a few times and then like we will so after iterating this rule a few times, we will reach the desired distribution mu. So this Glauber dynamics is very easy to implement and widely used in physics and computer science. And for this Ising model in the Glauber dynamics, we want that the mixing time is roughly linear in terms of the distribution. So the distribution is over like n atom, then we want the mixing time to be around n log n. And so generally, like we don't have a good heuristic to bound the mixing time of Markov chain, like especially for very large systems. So it's important to have a theoretical understanding of the mixing time of Markov chain. Okay. So specifically for the Ising model, and more specifically the Surrington-Kirkpatrick Ising model that I mentioned in like 2 slides ago, we do have some simulation for small system where we found that the mixing time is increased at the parameter beta, the inverse parameter increase. And moreover, there was a phase transition at beta equal 1, meaning that like for beta greater than 1, the Glauber dynamics on is very slow to mix. It mixes in time exponential in n. But for beta being smaller than 1, the Glauber dynamics is fast to mix, and it probably mixes in time like polynomial or even near linear in n. So people have this conjecture that like the Glauber dynamic will mix in time n log n when beta is less than 1. But for a long time, not even polynomial mixing time, so say t equals n to the 100 mixing time is null. And our work like established this optimal mixing time when beta is 1/4. Previously, we only know this optimal mixing time when the interaction matrix satisfies something called the Doppler condition, meaning that the L1 norm of J, which is like the sum of the absolute value of the n chi on like a row of J E at mode 1. And this condition is only satisfied when beta less than 1 over square root n. So our work is like a big improvement like on the magnitude of beta. So it's like a quadratic in n improvement. And this beta equal 1/4 is only like a constant factor away from the threshold beta equal 1. That is the conjecture. Okay, any question at this point? Okay. So I guess I will move. I guess after this point, I will move on to the technical side of like how to prove this conjecture. So this is our main result, and then after this, I will start talking about the technical detail of the work. Okay, so we are good. Okay, so we say that we can prove that when beta less than 1/4, we have this optimal mixing time. So what is the tool we use to solve this? So the technique of bounding mixing time of Markov chain is to solve the contraction of some measure of distance to the target mu. So suppose that nu t is the distribution S step t of the Markov chain. So after applying the rule for like t step, we arrive at the distribution nu t. So the question is how far away are the ratio nu t over m over mu. We can consider it as a vector in like the in like the space where like the edges are the state of the ground set. So we want to consider how far is this vector away from the on one vector. So yeah. And by contraction of measure, I mean that like after applying the so suppose we have some distance measure like d. Contraction means that like after applying the Markov chain operator on our distribution, so the distance between nu and mu after applying the Markov chain operator like reduced by some factor 1 minus rho. Then like if this whole, then like after apply in P for some, from maybe 1 over rho time, you will get very close. You will get that like, you know, the distance between mu with P raised to the rho and mu P raised to the rho is very close together. So that's the intuition of like why conduction conduction in distance will make the we make the vector nu and mu at time step t be close together. Okay, but we would want to formalize this. So there's a standard way to formalize this notion of distance. We call it an F divergence. So given a convex function f, the F divergence between the distribution nu and mu is defined as the expected value of f evaluate at the ratio like nu divided by mu, and is the expectation is taken like at all state f s according to the distribution mu, and then you take this expectation and minus it by f evaluate at the expectation of the ratio. So so it's kind of like you just exchange the order of the operator expectation in f, and this is like a so by transcending equality, because f is convex, so this distance is always non-negative. And some useful special case that of function f that people usually consider is the case when fx is x squared, then the distance this divergence or distance is called the variance distance, and when fx is x log x, then the divergence is called the Kumbach-Leibler divergence or KL divergence. Contraction in terms of variance divergence is related to something called the Poincare constant, which is again related to the spectral gap of the Markov chain operator. On the other hand, contraction in terms of KL divergence is related to a newer notion called modified loss-of-left constant that was established by Bovkov and Tatali. And contraction in entropy divergence is very useful for bounding mixing time of Markov chain. And that will come in the next slide. So the intuition of like the contraction factor and the mixing time is that mixing time is inversely proportional to the contraction factor. And so we want to lower about the contraction factor rho. So for the Ising model for good choice of starting point, then the F divergence is around log of 2 to the n, around 2 to the n for the variance distance, but around log of 2 to the n for the entropy distance. So this means that having a good lower bound on the entropy contraction leads to a better bound on mixing time, because like this, so on the variance side, you only can bound the mixing time by n divided by 1 over by rho variance. But then on the entropy contraction side, you can bound the mixing time by log n divided by rho entropy. So if rho variance and rho entropy are roughly the same, then by bounding the entropy contraction, you are earning like a factor of n in the mixing time. So so bounding like entropy contraction factor is very useful, but the problem is that it's usually a lot easier to establish variant contraction, because like as I said in the previous slide, the variant contraction is related to the spectral gap of the Markov chain operator. The spectral gap is something like like a difference between the top and the second lattice agent value. So bounding this means you basically only need to compute the spectrum of a matrix, and this is not hard to do. But there is just no easy way to compute the entropy contraction factor. The entropy contraction factor. So also, like entropy contraction, also besides from implying mixing time, it also implies other useful phenomena like concentration and hyperconductivity. And this was established by the paper above commented highly. So in the previous slide, I said that we need to know about the entropy conduction factor. So it was a known fact that like entropy conduction is strictly less than variant conduction. And for many models we care about, usually entropy conduction is like at least the variant conduction divided by some constant. So we want to establish this type inequality. And in order to establish this, usually previous work would require something called the marginal lower bound. For the Ising model, it means that the marginal of the spin I being set to plus or minus condition on any arbitrary configuration of the remaining spin will be at least some small constant. But unfortunately, this doesn't hold when the external field H is large. Another way to establish this this lower bound entropy conduction is through proving that mu is a very strong high-dimensional expander. This is by the work of Cry and Glauber in Fox 19. But again, this also doesn't apply to us because this strong high-dimensional expander assumption doesn't hold when the interaction matrix is anything non-zero. Okay, so in order to establish this inequality, we introduce a new tool called entropy independence. And using this, we can prove the optimal mixing time for Glauber dynamics or Ising model. And moreover, you can think of entropy independence as a way to relate the to lower about the entropy conduction in terms of the variant conduction. So here's our main result that we prove that the entropy conduction is about order 1/n. So this would be like some off by some constant factor, maybe 1/100 n. When the spectral norm of the interaction matrix J is strictly less than 1, and we establish this for all external field H, and this result is actually tight. So this condition that like when J is less than 1, then the entropy conduction is 1/n is tight, because so there was some example when the spectral norm J is exactly 1, and then you no longer have fast mixing. So as a consequence, for the SK or Sernton Kirkpatrick Ising model, we established that this had optimal mixing when beta less than 1/4, because for the Sernton Kirkpatrick Ising model, when beta less than 1/4, then with high probability the interaction matrix has spectral norm at most 1. Okay, so this is like some prior work and history on this problem. So for the very simple model like Curry-Weiss model, it had been like studied for a while, but like bounding this 1/ρ entropy by n was previously mainly only known when the when the external field is 0, and then only recently that people start to study the more general like case when the interaction matrix has spectral norm at most 1, but still they can only take care of like 0 external field. And finally, we established that we established the optimal mixing time. So we have the optimal mixing time, and we also remove the assumption that the external field is 0. Okay, so that's the history and the motivation. And then next, I will introduce the notion of entropy independence and show how it is related to existing notions like such as functional log concavity. So, any question at this point?
Can you, June, remind us what's the like how does the external field come into the formula?
Oh, yeah. So it's like so external field is okay. So external so like the weight of the configuration is like exponential of the external field times the configuration. So this term, I don't know how. Okay,
Yeah.
maybe I
This
can.
H vector here, yeah. Right? Or
Wait, sorry. Okay, can you repeat your question?
so the external field is related to this H vector here. Is that right?
Oh,
That
yeah,
point?
external field
Yeah.
exactly the H vector. Sorry, I didn't make
Yeah.
it clear in the. So yeah, external field is the H vector.
Yeah. Yeah. Okay. Okay. That makes sense.
So
And
then like when external field is very large, then like this term can be very small because if you okay H is like 100, right? Then if you set sigma to minus, then this will be 2 to the minus 100, so it's be very small, and that's the why you have this very small marginal, and that just like ruin the previous work like it just create a barrier that previous work cannot handle when the external field is large.
yeah. Yeah.
Okay, I hope that's clear. Yeah, thanks for the question.
Yeah. No problem. And we had another question from Federico. What is hypercontractivity?
Oh, okay. Actually, yeah. I, actually, maybe I should have. Okay. So I mean, I think it's like what a concentration is, but hyperconductivity, I think it's something like. Uh, yeah, actually, yeah. Sorry, I should have studied that, but I mean, uh, okay, so concentration means like if you have something called Lipschitz function on the state space of the distribution, you want that the function is close to its expected value. Hyperconductivity, I think, means something like you also have a function and something about it's also something related to concentration. But yeah, sorry. I
Yeah. No, no worries. Let's maybe leave it at that. So some form of concentration.
okay. So, any question? Other question?
Yeah, I think that's all.
Okay. Okay. So I will go next to entropy independent definition. So okay, now we will define entropy independence, right? And we will switch gear a little bit and talk about distribution that are over a psi k subset of a ground set of psi m, and the the Ising model, which is a distribution over like plus and minus spin raised to power n, so it's like n vertices, it had like either plus or minus spin, can be considered a distribution of this form too. When you take m to be 2n, like one for each atom, like one plus and one minus for each atom, and then the configuration is a h psi n. So like it's like an equivalence thing, and this view of the distribution is just more convenient for our purpose. And now we define the k-to-1 Dow operator to be the operator that takes a set S of psi k and sample I and S uniformly random. So now 1 over alpha entropy independence is defined as follows. So for any distribution nu, we want that the Dow operator will contract the KL distance between nu and mu as follows. So if you contract by like this alpha over k, alpha times k factor, and then like why this entropy independence useful? So I guess if you know something, the framework called like local to global framework by Aleph and Low in Stock 20 and some other people more recently. then you will see that like you can sort of combine these inequality together to establish the desired entropy condition of the Markov chain operator, and that will imply lower bound on the entropy conduction factor, like rho entropy that I talked about in the previous slide, and that in turn that imply optimal mixing for Markov chain. Okay, so how is entropy independence related to other existing notions in the field? So entropy independence is weaker than a notion that was introduced earlier, called fractional log concave, and it's actually implied by fractional log concave. There's also another notion, maybe introduced in 2020, called spectral independence. And entropy independence implies spectral independence. But the thing is, many distributions that satisfy spectral independence can also be solved to satisfy entropy independence. Moreover, like while spectral independence can only be used to bound the variant conduction constant, entropy independence can be used to bound the entropy conduction constant. So it's very useful in establishing optimal mixing type of Markov chain.
June, I'm sorry, could you go back to the previous slide for a moment? And
Yeah.
here, can you say sort of maybe how should I intuitively think about this as being like a notion of independence? So it says that the marginals, their KL divergence is at most kind of a kth fraction of the whole thing, but why is this independence?
Yeah, sorry. So the reason we call it entropy independence because it's related to. So there's another way you can view spectral independence. So spectral independence, you can view it as like this. So if you remember what spectral independence is, spectral independence, okay. Then it's related to like something called the coordinate matrix, right? Being bounded by, has spectral norm being bounded by 1 over alpha. So some order one thing. This is the spectral norm of the coordinate matrix. And so this is sort of equivalent to like the contraction of like the 2-to-1 operator. So it's like 1 minus 1 over 1, I think. Like, yeah, so it's like, so it's the equivalent to this. So this usually viewed as a contraction of the 2-to-1 operator, right? But you can see that like the k-to-1 operator, like if you write out the matrix, then it has the same kind of contraction. I'm not sure how to say. So think about this, right? So you know what is a one skeleton walk? So you start at the element I, and you go up one element to go to ij, and go down to j, right? So this is called the one skeleton walk. But there's an equivalent way to do this walk, that is you start element I, and you go up all the way to S that contain I, and then S has sign K, and then you go down to J that are contained in S. So even down here you go from 1 to 2 to 1, and here you go from 1 to K to 1. That like they are still equivalent walk. Like if you just write out the matrix, you will see that the transition matrix from I to J is the same in this walk and in this walk. So this walk, like the down step here is operated by something called the 2-to-1 operator, where you just take a set of two elements, you select one set, like one element, you call it random, right? And the down step here is like k to 1 operator, where you take a set S and you select one element I from S uniformly at random. And so spectral independence means like this random walk has good entropy conduction, and that's sort of equivalent to not entropy conduction, sorry, variant conduction, and that is equivalent to good like x square conduction of the dk to 1 operator. So but because we call it entropy independence because we replace the variant the x square here with x log x, so this will be x log x. So that's why we go from spectral to entropy. Yeah.
So can you like, is it also equivalent to write like can you write your statement here as things that only compare this 1-2 walk? Like
you mean no, this equivalent to like 2 to 1?
Yeah.
No, the answer is no. So there are walk when you, so that's the thing with entropy, right? So it's pretty weird thing. So there are walk when the 2 to 1 operator have no conduction at all, but the k to 1 still has this alpha k, like not walk, but sorry, distribution mu. So there is this mu where like dkl of nu and mu is pretty much equivalent to. Okay, so it's a mu2 and mu2, mu2 d21 and mu2 d2 to 1. So that there are some distribution where like these two things are like have very small difference, but this thing is still hold. So somehow like k to 1 is the right notion here, not 2 to 1.
Yeah.
Okay. Yeah, sorry, like this may be not super technical or not clear.
Well, maybe it's not so nice for the rest of the audience. At least it's making a little bit of sense to me. So I think there is something I'm a little bit confused about with these operators, which is just like, why is this the direction? Like, why is it that I want to say...
Yeah.
Okay, so it's like if basically I'm saying they're approximately independent because the kind of coordinate-wise, let me think about the variance distance. The coordinate-wise variance distance accounts for most of the distance. Is that...
coordinate. Yes. I feel like in this case, wouldn't it say that the coordinate wise distance is a small part of the total distance?
Oh yeah, so it's the other way around. Okay, I think
it's
that's
the other
what's
way around.
confusing me about this. So why is it this direction is independence?
Yes. Okay, I see. Yes. So so first of all, it's always true that when you apply the operator, your KL distance is always less than the original distance, right? Like this is called the data processing inequality. So okay, so it's hard to say. Yeah, I couldn't think of it at the moment though. Like it is like very natural to go from the spectral gap bound to this formulation, and I don't think it makes sense to have that this is some less than inequality because it go against the data processing inequality. So yeah, so I don't know.
Yeah. Okay. Maybe I'll have to think about it a little bit offline. I think I think maybe if it's easy to, I think your equivalence down below should sort of explain it if I just understood actually why it's true. I think this is not really an issue that's specific to entropy, right? My confusion is just about the distances and
Yeah. So I think after this point, I will start talking about some. So I will start talking about an equivalent formulation of entropy independence that is purely in terms of the generating polynomial of the distribution, and so it will become very algebraic, and then this view of entropy will be sort of lost. So I'm not sure if like moving on from this point will improve your
Sure.
understanding of
Let's move on, and then we can always. Maybe I'll ask a question at the end if I'm still confused.
Okay, so yeah, thanks for the question. Yeah, I think it's sorry the intuition wasn't so clear. So yeah, and I just said so. So there was some previous notion, and entropy independence is like something called fractional log concave, and something called spectral independent. Entropy independence is like in between them, and it actually seemed to be the useful thing because it can be used to establish like it's useful to know about the entropy conduction, and with that establishing time missing time for global dynamics and other random walk. And then the concrete application for entropy independence include like counting Martini in planar graph, linear time generating random spanning tree, or random forest of a graph, and also something called non-symmetric determinant point process. So yeah, I just bring a bunch of application here to see if it ring a bell. Also, so this is a side point. So entropy independent established like entropy conduction. So it can be also be used because there was like a standard way to go from entropy conduction to concentration. So it can also be used to establish concentration. But there's an alternative route that go from the weaker notion of spectral independence to concentration. Actually, this needs something slightly stronger than spectral independence, and this is a work by Rasmus and Kaufman and Soda, and this will be in Soda this year. So just mention it here because yeah, it's another way to establish in this concentration. So I will show an alternative way of viewing entropy independence, and with that way it will be clear to see like why we had this implication from fractional log concave to entropy independence. So first we need like some definition. So we define the generating polynomial of a distributed mu to be a polynomial in n variable. It defined as the sum of mu s times the product of ci for I in S. So think about this f mu as an extension of the distribution mu on R to the n. So it turns out that we can view entropy independence in terms of the geometric property of this generating polynomial. So we define h to be log of f evaluated as di raised to the alpha. Define pi to be the marginal of I, of element I. And this will be the same as the partial derivative at I of h evaluated at the on one point. Then we also define g to be f of zi raised to the alpha, and then raise the entire thing to 1 over k alpha. So this is pretty weird definition, but the point is that we want to keep this function g to have degree 1 to have total degree 1 in z1 to the n. So we want to keep it homogeneous of degree 1. And in that case, when we define g like this, when g is homogeneous of degree 1, then h is concave if and only if g is concave. And this h being concave is equivalent to the fact that like f is alpha fractionally log concave. Okay, so we can view entropy independence as the fact that g is bounded above by the tangent vector at on one. So this inequality is like g s z1 to the n at most sum of gi times pi. And okay, so pi is the partial derivative of h, but also the partial derivative of g, if you scale things in the correct way. And fractional log concave is equivalent to the fact that g is concave. So here it's equivalent to like at every point of the positive orthon, you have this tangential bound. So it's clear from this formulation that the fractional log concave is stronger than entropic independence. And what is spectral independence? This is equivalent to the fact that G is locally concave at the on one point. So if you view it in the geometric way, then it's clear that why this imply this and then this imply this. Okay. So I guess this is the intuitive picture, and then the actual formula is restated here. And alpha fractional log concave is equivalent to, so the log concavity can be rewritten in this way. And notice that here, okay, so this lambda is called the scaling factor, and here if you set lambda to be on 1, then you recover the inequality above. So that's why alpha fractional log concave is stronger than entropic independence. Okay. Yeah, so so I have 50 minutes left. I think I could prove I could prove why this equivalent formulation for entropic independence makes sense, and then I can quickly go over like how to apply entropic independence for Ising model. Okay, so we want to solve like why this tangential inequality imply this entropy conduction of the K to 1 operator. So the way to go is first we fix the right hand side of the equation here. So we fix this to be, but then like the way we do that is we fix new dk to 1 at some vector q, right? And now we want to minimize the left hand side, subtract it to this condition. So through like through some convex programming like argument, we will see that like the minimizer for the left hand side, the new minimizer left hand side will be like a scaling up mu. So it will be this form. It will be mu s times lambda. Okay, so this will be lambda. Sorry, lambda I for I in S for some vector lambda in R to the n. Okay, and this so we can rewrite this minimum. So the way to see it is we use the Lagrange multiplier, and we can rewrite this minimum as the minimum over this function phi nu, and then like after rearranging things, we will see that the function phi nu can be again rewrite as the log of the quadratic polynomial of mu. So this f is f mu. Plus some term that is, sort of to think about this. Yeah, so we will be plus some other term. Okay. Okay, so now we can rewrite this function as like so this minimizing problem as minimizing over f plus some like log of f plus some other term. So now to do this minimization, we sort of need to maximize exponential of new phi of nu. And now because we have the tangential inequality here, so we can apply f. We can apply the tangential inequality, right? And then we can set yi to be qi over pi, and then after some rearranging, we get back the design inequality. Yeah, so this is like, I guess it's a pretty tedious technical proof, but the idea is you can fix the right hand side first, and then put prove the inequality by rewrite it as a convex optimization problem, and then the convex optimization reformulate the left hand side in terms of the transiting polynomial, and then you can apply the inequality here, and everything fall into place. Okay, so then we introduce entropy independence. So we want to show how this can be used to bound the mixing time of Ising model. So I will skip over this part. So this is for bounding mixing time of other related like local walk, but could be skipped here. So for Ising model, like there was the previous paper by Eldan, Kohler, and Yatoni, so that you can reduce the problem to bounding the entropy contraction factor only for matrix J of rank 1, where J is U transpose U for some vector U. And so to deal with this case, we need to prove something like this. So for this case, we want to prove like n, I guess n over 1 minus u squared mixing time. And so the standard notion of entropy independence that I introduced earlier actually couldn't give us on the way, like mixing up this linear mixing time. It can only give us some big polynomial mixing time. So we need to modify the notion a little bit and introduce some more complicated notion called non-uniform intermediate independence. So I'm not sure if we can go through this. Okay. Okay. So again, let mu to be not sure. Let mu to be the distribution on the spin plus minus 1 raised to n, and so for each vertex I, we define mu I to be the marginal of mu on the spin of vertex I of the ith vertex. So if you consider the plus spin at the blue ball and the minus spin at the gray ball, then mu I distribution over these two balls here, and we define like non-uniform entropy independence by like allowing the parameter like alpha I with like the distance between mu I and mu I to be different. And it looks complicated, but if you replace all this alpha I by the same alpha, then you will recover the same uniform entropy independence notion that was defined previously. Okay, and then we will show that the down operator has like 1 minus u squared divided by n contraction, and we will solve this by induction on the size n of the model. And the way to go is we take a spin I and we condition on it being like either plus or minus, and after this conditioning, we will still get back an Ising model with the interaction matrix still being like rank 1, but the vector update to be like u of minus I, which means like u where the anti-I is deleted. And by applying that, so then we can apply the induction hypothesis with like n minus 1 vertices, and we get this inequality, right? So we can sum this inequality over the plus and the minus spin according to some weight, so that we almost recover the KL distance between mu and mu, but we are off by this term like KL of mu I and mu I. So remember that mu I is the marginal on the ith spin. Sorry, on the ith atom. That was defined in the previous slide. So we will get this inequality. So we almost there, but we have this weird term in orange, and then this thing in blue should be the norm of u instead of the norm of u minus I, right? So the natural way is we take the average over I, and in this way, like when we sum this 1 minus 1 over minus norm of u minus I, we will get back like 1 minus norm of u, basically. And then this part where we have the k-divergence between mu I and mu I, we want to compare it to the k-divergence between mu and mu itself, and this is where the non-uniform entropy dependence come into play. So yeah, so that's like the idea of how you go from non-uniform entropy independence to conduction of the Dow operator. And then the last slide, I will just show how to establish this non-uniform entropy independence, but that requires like the one more idea that is from like so we will previously we saw that like fractional log concave imply entropy independence, right? And so we will solve fractional log concave for the Ising model. And so we noticed that like scaling the Ising model by some external field lambda is equivalent to changing these the vector h. So they're both called external fields. That's what they are sort of equivalents. And then so we only need to show that the Ising model is spectral independent regardless of external field. And to show spectral independence, we need to use the previous idea of like going from the bound of the dot, going from bound on the dot of the dot producing matrix to spectral independence. But this part is quite technical, so let's skip that.
Can I ask here? So I think I missed. Why are you saying that you only need to show spectral independence here in the end?
Yeah. So okay. So fractional log concave is equivalent to spectral independence after you apply external field to the model. So this scaling thing, if you can show that this part is spectral independent,
yeah,
then you are done. Then for all lambda, right? Then this is equivalent to fractional log concave. So take a mu and then apply external field lambda. So lambda apply external field is like mu of S time product of lambda I for I in S.
Mm-hmm.
Okay, if you can show that this new distribution lambda star mu is spectral independent for all external field lambda, then it's the equivalent to mu be in fractional log concave.
Okay.
Yeah, and then like because applying external field you will recover back an Ising model with the same interaction matrix. So that's why like if you can show spectral independence regardless of external field, then you can show fractional log concave. Yeah.
Mm-hmm. Mm-hmm.
Yeah, but so yeah, I'm not sure. I think that's too technical, but some other application for this entropy independent framework include like parallel sampling for determinable point process. I guess I didn't really introduce this part, but if people know, then yeah. And also like faster sampling in like I guess optimal sampling in terms of amortized time, and also faster sampling for spanning tree. So previously we can sample like random spanning tree of a graph in time linear in the number of edges, right? But with entropy independence, we can show that we can do some pre-processing and then sampling random spanning tree in time linear in the number of vertices. But yeah, so that's some additional like preview for later. Okay, yeah, thanks for inviting me, and I hope that you guys have something else to talk.
Thank you, June. So let's thank the speaker, and maybe we can see if there are more questions. I guess we had a few along the way. I'm tempted to ask you a little more about this local to global thing, but I think let's leave it for after the session in case the audience has to go somewhere.
Sure, I guess I can stay at one of the table and chat.
Yeah, that's perfect. All right. So do we have any questions? Last chance. No. All right. So let's thank the speaker.